Hello! As promised in the previous video, we will continue introducing UART communication with a practical example. Adam, can you tell us what exactly we are going to implement?
Welcome back, everyone. We're going to implement a cooperative drawing game. We will need two development panels with buttons and a display each. We will be able to draw a line on the displays, which we can control with the buttons. The twist will be that both players can control the brush on their own and the other player's display simultaneously. So, players can draw a line together.
I can't wait to get started.
Let's start with an overview of the UART peripherals of the microcontroller. The STM32F4 family of microcontrollers that we are using includes two UART peripherals as well as 4 additional full USARTs, which are a relative of UART devices capable of synchronous communication. USART peripherals are higher order in terms of knowledge, as they can operate both synchronously and asynchronously, depending on their configuration. Here, I will show you the settings of the white Nucleo F446 panel. If you're interested in the configuration of the other panel, you can read it in the written curriculum available at crystalclearelectronics2.com. Import the Lecture 10 UART example code in the usual way, then open the .ioc file. You can see that most of the settings have already been covered in the previous chapters, but on top of the microcontroller layout, there are two previously unknown outputs. The PG9 and the PG14 legs are configured for USART peripherals. Click on USART 6 under the Connectivity menu. Here you can set the parameters you want to use the peripheral with. There are a variety of communication modes that the controller supports, which can be found in the Mode drop-down menu. In this case, and often in general, choose asynchronous. This determines that your USART peripheral will function as a UART. In the previously mentioned flow control, the RTS and CTS pins are turned off. Below, in the peripheral parameter settings, you can specify the baud rate, the length of the data, and the frame settings you want to send. As you can see in the picture, our communication will work with 115,200 bits per second, 8 bits of data, no parity bits, and only one stop bit. The configuration we are using is very common and is commonly referred to as 8N1. It's important to note that if you do not need bidirectional communication, you can configure the peripheral to be either send only or receive only. The last setting determines the oversampling. For STM32 microcontrollers, the default setting is 8 samples per bit time, but if the device is capable of it, it is more practical to use the larger oversampling, so we set this to 16 samples.
Wait a minute. So far we haven't mentioned oversampling. Let's see what it is.
Oh, didn't we talk about that in the previous video? Oversampling means that the microcontroller does not determine the value of a bit based on a single measurement, that is a single sample, but checks the input several times during a bit period and determines whether a 0 or a 1 bit was received in that period based on the values read. In addition, oversampling helps the receiver more accurately determine when a bit's state change occurs to better synchronize its clock signal with the senders. We've looked at the UART settings, but before we get started, Balázs, please help me demonstrate how to connect the two devices.
Alright.
The two development boards can be connected via the UART TX and UART RX outputs. The TX leg of one panel is connected to the RX leg of the other, and vice versa. If you want to test the program with only one device, connect the TX and RX outputs on the breadboard through a 10 kilo ohm resistor so that you will receive the data transmitted from the TX leg of your module, essentially talking to yourself.
There may be a condition during the power-up process where one leg is powered and the other is grounded, which can cause a short circuit. This is what the resistor is designed to prevent. Is there anything else we missed?
Yes, there is. I've almost forgotten, thanks for reminding me. The microcontroller decides whether a logic 1 or 0 has just been received based on the voltage at its input. The microcontroller measures this voltage relative to its own ground point, which is GND. For this reason, it's essential here to make the ground point of the two devices common. Find the GND outputs on both devices and connect them with a wire. After setting up the peripherals, let's get to the code. Like all peripherals, the UART must be initialized before use. The code snippet is shown on the screen starting from line 31 of the usart.c file. You may all be familiar with the set values. This file will be generated by the development environment based on the .ioc file that was previously set. The other new features are listed in the main.c file. At the beginning of our program code, briefly define the values needed to run, declare, and initialize the variables. Then we use the while1 infinite loop to read the state of the buttons. The direction defined by the buttons is stored in the variables x velocity and y velocity, and then the data corresponding to the button press is also passed to the variable tx data byte to be sent.
You may remember from chapter 9 that the origin of the display is in the top left-hand corner. Accordingly, in the vertical y direction, the up button is a -1 and the down button is a +1 step, and in the horizontal x direction, left is a -1 and right is a +1 step.
The lines of code implementing the sending and receiving of the data are then shown. The HAL UART transmit function is responsible for sending the data. It needs 4 parameters. The first one is the pointer of the peripheral we want to use, in our case UART 6. We must then specify which memory address we want to send from and how many bytes. In this case, we pass the tx data byte pointer to the function and specify 1 byte so that it will send out the value of our 1 byte long uint8 t-type tx data byte variable. The last parameter specifies the maximum time the program should wait for the transmission. The HAL UART receive function is used to read the incoming data. Again, we need to specify which peripheral we want to read from, which memory address to read to, and how many bytes to read. We use UART 6 and read 1 byte into the rx data byte variable. The last parameter here specifies the maximum time the program should wait for new data to arrive. Finally, it's just a matter of implementing the changes we made and received, and draw the new point on the display. Balázs, please upload the code and let's see what happens.
If I see it correctly, LED 3 is flashing. Can you tell me what it means?
Of course. Each run cycle is indicated by a status change of LED 3. This is called the heartbeat signal and is used in cases where we need to be able to detect that the program works correctly. It can be observed that when the communication is broken, the heartbeat rate is slower than if two devices were connected.
How does it work? What slows down or speeds up the flashing of the LED?
The reason for this phenomenon is due to the HAL UART receive function. An important parameter of this function is UART RX timeout, which is currently set to 200 milliseconds. This determines the maximum time the function waits for new incoming data. If information is received sooner, the function will finish, but in the case of a missing connection, no new message will be received, so the function will time out and wait for 200 milliseconds. If you use a single development board with connected RX-TX legs, you will find that all the drawing operations you want to perform happen twice, which is best observed by pressing the button on the side. First, the value is changed by pressing the button, and then by the data received by itself on the UART.
So, what shall we try to draw, Adam? How about a Mona Lisa for a challenge?
Good for a challenge, but I'd rather try a little house first.
Alright, let's get started.
Okay, then I'll start drawing the side of the house. This will be the top, and this is the bottom. Let's draw the line. Balázs, this is supposed to be a cooperative game, but for some reason I feel that you are deliberately trying to prevent the completion of the house.
I don't know what you're talking about. I'm just trying to add the artistic value of the image.
Of course. Have fun, and thank you for joining us for a practical demonstration of UART.
See you in the upcoming video, where we'll learn about CAN bus communication, which is widely used in the automotive industry.
Bye.